Welcome to the Problemas channel season 2 episode 18, the episode which I have titled Now You Know Me and Now You Don't, because that title is also a hint for the mathematical problem S2E18, which solution I will share with you in this episode. Before I do that, however, as a traditional friendly reminder, if you're joining our channel mid-season, then first of all, thank you very much for your vote of confidence and welcome to our channel. And second of all, it is a good idea for you to go to the homepage of this channel and in the channel's trailer section find the episode titled The Problemas Channel How To, and watch that episode in its entirety. That episode is not too long, it's about 20 minutes or so, and follow all the instructions that we give in that episode, because in that episode we explain and motivate everything that we do on this channel. The challenge of the mathematical problem S2E18 is to solve the equation that is written on the board behind me using the equation problem solving approach. In the previous episode, we explained that if we want to solve this or that technical problem using the equation problem solving approach, then we are first to introduce as many variables as needed. Then, using the variables that we just introduced, we are to construct as many equations as possible, and in general we should balance not only the quantity but the quality of the constructed equations against the nature of the problem at hand. As the third and the final step, we are to solve as many equations as possible, and the process of solving an equation or the process of solving many or a system of equations entails the fact that we need to prove that we haven't missed a single solution and that we have generated all the possible solutions. Once these solutions are attained, we need to square these solutions against the specific nature of the problem that we're trying to solve and make sure that these solutions make sense. Now, some of our viewers may look at the mathematical problem S2E18 and say, Roman, what are you smoking and what kind of tea you're drinking? You already gave us an equation. That equation is an algebraic equation in a single, most famous unknown of all times, x. So it seems that there is no room for the application of the equation problem-solving approach. And this is exactly the crux of the matter, and that is exactly why I brought this problem to your attention. And let us now, before I show my solution of this problem, let us look at what many students will do in this case. The first step that is pretty much guaranteed that every person who takes on this problem will do is square both sides of this equation. Let us do that together. X squared minus 5 squared will yield x to the fourth power minus 2 times 5 times x squared plus 25 is equal to x plus 5. And here, as a natural next step, most students will collect all the material in this equation on the left hand side of the equal sign, leave 0 on the right hand side of the equal sign, and they will obtain the following equation: x to the fourth power minus 2 times 5 times x squared minus, we'll put x over here, plus 20 is equal to 0. And at this point, again, many of our viewers will wonder, why did Roman give us this problem? Because the variable is already introduced. There is no room to introduce our variable, it seems. And all we have over here is the so-called depressed quadratic expression and or depressed quadratic equation in a single variable x. And many of the viewers who watch this channel on a regular basis already know what I'm about to say. It turned out that in the grown-up mathematics, there exists a connection between the ability to write down the expression for the roots of such a polynomial or algebraic equation ahead of time using a finite number of additions, subtractions, multiplications, divisions, and root extractions, and the so-called finite alternating and finite alternating groups and their parents groups, which are called symmetric groups, or the groups of all possible permutations of a finite number and distinct objects. It can also be shown that that connection manifests itself in the idea of solvability of these groups. For example, if such a group, for example, Sn is solvable, then the expression for the roots of the algebraic expression, of the algebraic equation, can be written down ahead of time in radicals, which precisely means that such an expression will contain a finite number of additions, subtractions, multiplications, divisions, and root expressions. And if the corresponding group, for example, this guy right here, is not solvable, then the expression for the roots of the corresponding algebraic equation of order n cannot be written down. And the idea behind the solvability, or a definition of a solvability of a group, can be done in a couple different but equivalent ways. For example, one way in which the solvability of a group can be defined is using the notion of the commutator subgroup. And according to that definition, if the nested chain, or what, for example, in Russian we would call a matryoshka, if the chain of nested commutator subgroups of the commutator subgroups, and so on, of the parent group terminates with the trivial subgroup of the parent group G in a finite number of steps, over here the number must be n and it must be finite, then the corresponding group is solvable. But if this nested chain of commutator subgroup over commutator subgroup does not terminate with the trivial subgroup in a finite number of steps, then the group is not solvable. Again, it can be shown using relatively highbrow mathematics that the first alternating group that is not solvable corresponds to number 5, and the previous groups, for example, A3, A2, A3, A4, are solvable. Consequently, the complete symmetric groups S2, S3, and S4 are solvable. The symmetric group S5 is not solvable. And that all means that, for example, for the quadratic equation, algebraic equation in single variable, it is possible to write down the expression for the roots of such an equation ahead of time that contains nothing but a finite number of additions, subtractions, divisions, multiplications, and root extractions. And in some sense, the indoctrinated audience who knows all this highbrow mathematical machinery knows that such an equation can be solved. There is no technical or fundamental challenge. It is possible to do that. However, the manipulations that involve the process of recovering the values of these roots is quite clumsy. It is error prone, and let's say even by the looks of this specific algebraic equation, because it's missing the third power of x, again, it looks like the roots of this equation sum to 0. That observation can be spun tactically into a useful manipulations, and the corresponding expressions for the roots can be written down. However, if we take, for example, for granted that certain formulas for the roots of this polynomial equations already exist, then the process of inserting specific numbers into a formula that was discovered generated or cooked up by someone else does not constitute the process of doing mathematics. And even if you know how to do that, you still will not be solving this problem using the equation problem solving approach, because you will not be introducing any new variables, you will not be solving new equations, and thus, in some sense, that violates our requirement that this problem needs to be solved using precisely the equation problem solving approach. Now, I will share a few philosophical thoughts um, that are generated by this problem, and they will show exactly why I brought this problem to your attention. But the next segment will be optional. The impatient viewers can skip the next segment and go directly to the solution, to my solution of this problem. This segment is optional. It is for curious travelers only, because in this segment I will share my mostly philosophical ideas about why the mathematical problem S2M20 is worthy of your attention. In order to solve the mathematical problem S2M20 using the equation problem solving approach, we will generate an idea or a thought that is both counterintuitive on the one hand, yet productive on the other. And it is the very existence of such situations when such thoughts that are counterintuitive on the one hand yet productive on the other is, in my view, one of the reasons why making a deep, meaningful, and interesting discovery across all hard sciences, be it mathematics, theoretical physics, or computer science, is so difficult. And the foundation of this difficulty, or one of the foundations of this difficulties, is what I refer to as a mental or an intellectual inertia, or our unwillingness or maybe inability to peel ourselves away from the material that we think we know and understand well, and look at that material under a new angle, in the new light, and generate precisely an idea or a thought that is both a counterintuitive on the one hand, yet productive on the other hand. In order to demonstrate how this idea may work in practice, I will share two examples with you. One example will be from theoretical physics, and the other such example will be from mathematics. In theoretical physics, Isaac Newton published his Principia in the year of 1687, if I'm not mistaken, and starting from that time, the people who were doing theoretical physics of the period, it looks like reasonably quickly realized that the model that was suggested by Newton describes the physical phenomenon in the observable universe within, of course, certain limitations very, very well. And again, it looks like these people realize that the Euclidean geometry is the geometry that explains or models the visible universe, again, within certain limitations very well. And it looks like, again, that many people got comfortable with the idea that time flows at a constant rate. Now, how do we know that that was the case? Well, Albert Einstein published his first groundbreaking work on his theory of relativity in 1905. That was his first publication, and the next one followed 10 years later in 1915. So the question is, why literally for about 200 years no one was able to come up with the ideas that Einstein came up in 1905? And again, there are many reasons, of course, and some of them are technical, some are historical, but I think one of the reasons why that was the case is precisely because of the intellectual inertia or unwillingness, or maybe inability of the participant or participants of the game, to which we refer as theoretical physics, precisely look at the material that they thought they understood well, knew well, and learned well in a new light, under a new angle, and generate an idea that is both counterintuitive on the one hand, yet productive on the other. And it took, as we know historically now, someone like Albert Einstein to basically come in and say, guys, look, there exists non-Euclidean, or maybe a non-Euclidean geometry provides a model that explains the phenomenon and the observable universe, again, within certain limitations and within certain contexts, for example, in the presence of large masses, better or much better, more precisely than the model that is suggested by the Newtonian formalism. That is the situation with intellectual inertia in theoretical physics. Switching gears and looking back at mathematics, in my free book, Group Theory for All, an elementary introduction to the theory of groups, which I published on Quora in the last discussion in the last chapter, I share a little bit of a history of the complex number to which we refer these days as I, with the property that I squared equals to -1. This construct right here. Turns out we have documental evidence that, again, in Western civilization, in Western culture, it was the ancient Greeks about 2,000 years ago. They actually stepped for, as much as we know, for the first time, again, in Western Europe, in Western civilization, on the process of extracting a square root from a negative number. Let's say that number was -1. It was not really 1, but for demonstration purposes, let us agree that it was 1. Back then, again, the intellectual inertia that apparently overtook these people did not allow them to see what they actually were dealing with. They thought that this was a mistake. They brushed this idea away. And again, it took several hundred years for, again, a constellation of flamboyant Italians to come up with the algebra of the numbers to which we refer now as complex numbers. And it took the Norwegian land surveyor known as Caspar Wessel to come up with the beautiful geometry of complex numbers. And nowadays, complex numbers play an important role not only in the entire mathematics, but they travel well outside of mathematics. In physics, for example, one of the facts that is very interesting and valuable that we learned in complex analysis is that a product of two non-zero complex vectors is, again, non-zero complex vector that lives in the same parent plane. That is why, for example, among other reasons, complex numbers make their way into quantum mechanics. To summarize, the ability to generate ideas that are both counterintuitive on the one hand, yet productive on the other, is a good skill to develop and nurture, because many times in mathematics we will have a hard time solving a problem, even though that idea that will unlock a beautiful, elegant, crisp solution of the problem precisely possesses these two seemingly contradictory properties. Such ideas are counterintuitive on the one hand, yet they are productive on the other hand. And this is exactly what we do in the next segment, when we will solve the mathematical problem S2E18 using the equation problem solving approach. Now that we know about the existence of ideas that are both counterintuitive on the one hand, yet productive on the other, let us see how the process of generating such an idea can look in practice. In order to come up with a beautiful, elegant, and crisp solution of the mathematical problem S2M20 using the equation problem solving approach, this idea that is counterintuitive on the one hand, yet productive on the other, can be generated as follows. Let us look at any of the equations presented over here and concentrate on the objects to which we refer as constant numbers. What are the constant numbers in this equation, for example? Well, the constant numbers in these equations that we see are the following: 4, 2, 5, and these two constant numbers form a product which forms a slightly more complex constant number, 10. This is a constant number 2. This is a constant number 25. This is a constant number 5. In the equation shown over here below, the constant numbers are 4, 2, 5 again, 2, 20, and 0. So here, the idea that a mathematician will generate comes down to the following. We take something that we do know, and we know what is 5. This is a constant real number. It is not unknown. It is known to us. But counterintuitively, perhaps, we take that constant number and we demote it into an unknown. Let's say we will name that number as z, like so. And that is fundamentally that the idea that we were trying to elicit from you. This is the idea that you were expected to generate. And at the same time, this is the idea that explains the title of this episode. Now you know me, and now you don't. In other words, here thinking like a mathematician, now you know me, number 5, now you don't. Now the 5 becomes an unknown z. After we generate this idea, and that the process of generating this idea constitutes the process of doing mathematics, this is where the mathematics with the capital M ends, and what follows is what happens after mathematics with the capital M leaves the room. In other words, after the process of generating this idea, what follows is some amount of symbolic shuffling and computational calisthenics, and at the same time, this symbolic shuffling will either validate or invalidate our idea, and it will, in some sense, dole out a verdict saying, yes, that idea was fruitful and productive, or no, that idea was not thoughtful and fruitful and it was not productive. Let us see if it is so. Here, when we, let's say, for example, we will not need this guy, this equation, I'll erase it. We'll work with this equation right here. We will rewrite this equation using this idea of taking what we know, 5, demoting it into unknown, z, and then translating the equation that we have over here into the symbols of the unknown z. Here again, some taste and some experience is needed in order to decide which numbers to translate into the unknown. For example, number 2 over here, we will not translate in terms of the number 5, and number 4 shown over here, we will also not translate. We will leave it alone. Now, this translation then will yield the following. X will still be to the 4th power minus 2. The number 2 we will leave alone. Here, instead of 5, we will use our unknown z, like so. I'll use a different color so it's easier for you to see. Times, this object remains the same, x squared, plus 25 we will translate. If 5 is an unknown, then 25 is even more unknown to us, so to speak, because it's much more complex formation. Now we need to square this guy. 25 translates to 5 squared, so in new symbols that's z squared. The rest remains so far the same, equals to x remains plus remains, but instead of 5 we write down our new variable z. What we used to know, now we know you, now we don't. And in order to make it easier for you guys to see this transition, I'll just use these arrows right here to show that 5 was demoted into z, 25 was demoted into z squared, not known. This 5 was demoted into the z, and now what do we have? Now we take our original equation and we turn it on its head, but all the while, what did we do with all these manipulations, aside from thinking like a mathematician? Exactly, we executed the step number 1 of the equation problem solving approach, where we did what? Where we introduced as many variables as needed. So far, we have one variable, z. And in some sense, we can say that this whole problem can be represented or possesses 1 degree of freedom. So with one variable, we think we can solve this problem. Now, let us rewrite this equation in terms of the new symbol z, going from the most senior exponents or from the most senior powers down. So what will we have? We will have z squared as the first term. Then we will have negative 2x squared z, and one copy of z, 1 times z over here. When we carry this summand over the equal sign from the right-hand side to the left-hand side, what will happen? This sign will flip to a minus. We have a minus here, so if we put minus over here, I'll use also red just to make sure that we'll understand negative comes out from both summands z and z over here. And what will we have in parentheses in front of z? Exactly, we'll have 2x squared plus 1 times z. Then what we'll have? We will have the most senior formally unknown term plus x to the fourth, plus we'll have this guy when he jumps over the equal sign from the right-hand side to the left-hand side. He takes off plus, puts on minus, and becomes negative x. And now all this beautiful mess is equal to what? All this beautiful mess is equal to 0. And look at the magic. In terms of the new unknown z, this equation over here becomes quadratic. And we all know, starting from the middle school or earlier, how to write down the expression for the roots of the quadratic equation. And again, one more time, just to make sure that we're all on the same page. In this process, if we partition it into real or mathematics versus not mathematics, the process of generating this idea that is counterintuitive so far, whether it's productive or not, we do not know yet. We will discover it in the next small number of minutes. But so far, generating this counterintuitive idea is what constitutes mathematics with a capital M. What follows now, this, and everything else that follows is not mathematics, but computational calisthenics at best, or what happens after mathematics, after the generation of idea or a generation of thought walks out of the room. So now we all know how to spell the roots. Let me use the red chalk. Z, 1, 2, that will be 2 roots. Let's see what these roots are. What will they be? Negative b, so we will have 2x squared plus 1 plus minus square root of what? Square root of b squared. So it will be 2x squared plus 1 squared minus 4 times a, which is 1, times c, which is x to the fourth minus x. So negative 4x to the fourth plus 4x. So far so good. This is nothing earth-shattering. This is typical middle school arithmetic. Divided by 2, 2a. A is 1 divided by 2. And what remains to be done here? Well, again, a mechanical or almost thoughtless, as far as mathematics with a capital M is concerned, process, or as mathematicians would say, a straightforward finite computation. Let's unfold this expression under the square root and see what happens with it. So let's carefully write down 2x squared plus 1 squared minus 4x to the fourth plus 4x comes out to what? Let's do this together. That would be 4x to the fourth plus 4x squared plus 1 minus 4x to the fourth plus 4x. What will happen now? Let's observe that the fourth powers of x cancel out. They enter into this expression with the opposite signs. And what do we have now? 4x squared, 1, and 4x. Do we need paper for that? No, we do not need paper for that. 4x squared plus 4x plus 1 is a synonym for what? Exactly, it's a synonym for a perfect square. 2x plus 1 squared. So far so good. Now, because this expression came out to be a perfect square, what do we have then for the roots of the equation that is quadratic in z? Well, let's write it down carefully over here. z12 is equal to 2x squared, 2x squared plus 1 plus minus the square root of the perfect square will be absolute value of whatever is the square of is taken, but we have the plus minus over here, so we leave it as plus minus, and then it will have 2x plus 1 divided by 2. And now we just have to carefully spell out what that means. For the first root, we will have z1. What do we have? Let's write it down. 2x squared plus 1, let's say plus 2x plus 1 over 2. That will be what? 2x squared, 2x1, 1 plus 1 is 2. Factor out 2 from the numerator, cancel with the 2 in the denominator. What do we have? Exactly, we have x squared plus x plus 1. Was that difficult? No, that's not even mathematics. This is just middle school calisthenics. And what do I have for the second root? For the second root, we clearly have 2x squared plus 1 minus 2x minus 1 over 2. And what is this expression equal to? Positive 1 and negative 1 cancel each other out. 2 in the numerator and 2 in the denominator cancel out. And what do we have? In the end, we have x squared minus, what do we have? Minus x. And this is our second root, z. And now I ran out of the room on the board. I'll take a short break to erase and make some room for the final solution. But now we understand that we mechanically unfolded the equation that was quadratic in the variable z. We wrote down mechanically the formula that we remember. We carried out a finite computation. It came out to be a very pleasant computation. In the end, for the discriminant of this equation, we obtain a perfect square. Square root of a perfect square is the absolute value of that material that is being squared. But because we have plus minus sign over here anyway, we take it as it is. Taking the plus sign, we obtain this root for z, and taking the negative sign, minus sign here, we obtain that root. And now all we have to do is take this substitution and work it in reverse. Because you keep good records of the work that you're doing on this channel, and you are keeping track of the progress as we go along, you understand where these two expressions for the roots of the quadratic equation came from. I erased all the intermediate work on your right to make room for the final stretch. And here we will now do a reverse substitution, and instead of 5 on the left hand side of the equal sign, we will, instead of z on the left hand side of this equal sign, we will put precisely the constant number 5. So what will we have in this case? Let me just separate this, and then we will write x squared plus x plus 1 equal to 5. Again, this is the translation of this root of the quadratic equation. Instead of z1, we simply put 5 because this was our initial substitution. And now all we have to do is solve another quadratic equation. X squared plus x minus 4 equal to 0. Again, this is not mathematics. This is what happens after mathematics with the capital M leaves the room. The mathematics in this whole exercise, in the whole manipulation, was the idea, the happy thought, to go from what we know to and demote what we know into an unknown. Now we mechanically perform another finite computation and write down the roots, this time for x. Let me just highlight them maybe with blue. So x, 1, 2 for the first pair of roots. What do we have? -1, -1 plus minus square root of what? B squared is 1 minus 4a 1 c minus 4 over here. So 1 plus 16, 17, square root of 17 over 2. Was that easy? Was that straightforward? Yes, it was. We didn't even have to think. Again, this is not mathematics. Now, for the next pair of roots, what do? We take the second expression for the second root z of the variable called z. And again, instead of z sub 2, we substitute the original number 5. And what do we have? Well, let's write it down. X squared minus x is basically a synonym for 5. We now write another quadratic equation, x squared minus x minus 5 is 0. And with the blue chalk again over here for 3, 4. For the next two roots, let's write down this expression together. What will we have? This time, b is -1, so negative b will be 1 plus minus. What will it be? B squared minus 1 squared is 1 minus 4a. A is 1. 4 times 1 is 4. 4 times 5 is 20, taken with the negative sign. 1 plus 20, 21. So that will be a square root of 21, also over 2. And now we have 4 roots, x1, 2, x3, 4, of the original equation. We of course have to make sure that when we add 5 to any of these numbers, the square root, the operation of extracting the square root is valid. But for simplicity, let's say if we go back to this equation shown over here, we see that we recovered all 4 roots, and again they sum to 0, and done professionally with the free software called GeoGebra, I graphed. Here in a few seconds I'll show you the graph of which polynomial. The graph or partial graph of the polynomial, let me show you this guy, x to the 4th minus 10x squared minus x plus 20 equal to 0. Here, the graph, the partial graph of this polynomial, which shows the roots or the places where the graph of that polynomial intersects the real axis, the x-axis, will look as follows. Now that we have seen the 4 distinct real roots of the algebraic equation of order 4 shown over here, we remember that the third step of the equation problem-solving approach prescribes us to square or to validate the results or the solutions of the equations that we obtain against the specific nature or the concrete nature of the given problem. And in our original problem, we're not given the equation of order 4 as shown over here, but we're given a construct that looks as follows. And in some sense, we can see that over here, we expect to see 2 roots of this specific equation. Not 4 as shown over here, but 2, because, for example, we see that that graphically, for example, the left-hand side of this equation can be represented as what? Can be represented as a shifted parabola. If this is, for example, the real axis, if this is x, this is y, then the graph of this side of the equation can be represented as follows. When x is 0, this will be negative 5, and the graph of the right-hand side of the given equation, or the partial graph of that equation, is basically the representation of the square root that it shifted leftward by 5 units. So it will be somewhere right here, and the positive branch will run as follows, though this will correspond to 2 roots of the original expression, and our job is to filter out which one is which. And that process is again very straightforward. Here, originally I thought that I will leave it as an exercise to our viewers, but in the spirit of showing all the work that we do on this channel in a public setting, let us do this together in an expedient manner. Let's say the first root, x1, that is negative 1 plus square root of 17 over 2. Let us validate this root. So x squared 1 minus 5 will be what? Negative 1 squared will be 1. Square of the square root of 17 will be 17. 17 plus 18, 17 plus 1 will be 18. So we will have 18 minus 2 copies of the square root of 17 over 4, negative 5, so negative 20 over 4. What will we have? We see that 18 minus 20 will be negative 2. Negative 2 over 4 will be negative 1/2, minus square root of 17 over 2. So this is definitely less than 0, and this root is no go. We eliminate it. Now let's analyze the root number 2. When x1 is equal to negative 1 minus square root of 17 over 2, then x squared 2 minus 5 will be what? Here, for the purpose of raising this root to the second power, we can factor out negative 1, so we'll be squaring 1 plus square root of 17. So here we will basically have negative 1/2 plus what? Plus square root of 17 over 2, and the question is whether this will be equal to what? X2 plus 5. This will be what? Plus 5, 2, 10, 10 minus 1, 9. So it will be 9 over 2 minus square root of 17 over 2. And it is easy to see that the equality does hold. The easiest way to verify it is basically to square this side over here. When we square it, well, what we have? 1/4 minus 2 times 1/2 square root of 17 over 2 square root of 17 over 2 plus 17 over 4. I'm sorry, over 4. Why did I write 8? 17 over 4. 1 plus 17 will be 18. 18 over 4 is the same thing as 9 over 2 minus square root of 17 over 2. These expressions are the same. So this root is a keeper. So we write down over here, I'll use the green chalk. So in this case, the first root will actually be this guy right here, negative 1 negative square root of 17 over 2. So this is done. Let me erase this once we understand what is going on here. And now we just have to validate the second pair of roots that deal with square root of 21. That is also straightforward, as we did just a few moments ago. let us take care of this. So now we examine the root number x3. x3 will be 1 plus square root of 21 over 2. What do we have? For x squared 3 minus 5, what will we have? 1 plus square of 21, it will be 21. 1 and 21, 22. 22 minus 5 times 4. 22 minus 20 is 2. 2 over 4 will be 1/2. 1/2 plus square root of 21 over, what will be 2, guys? Over 2. Now, what about the expression which says square root of x plus 5? So x3 plus 5 in this case will be what? It will be 11. It will be 11 over 2 plus square root of 21 over 2. And the question is whether the square root of this is the same thing as this. Well, again, the easiest way to see is to square both sides and verify that the equality holds, and that is actually true. 1 plus 21, 22. 22 over 4 will be 11 over 2. Here I'm squaring this guy. Plus 2 times 1/2 times square root of 21 over 2. That will be square root of 21 over 2. This is an identity. Thus, we have our second root. Let me write it down over here. x2 will be 1 plus square root of 21 over 2. And it is evident already that the second root over here will not fly. But just to show that, let's consider it quickly over here in this section. Let's analyze the root number x4. That's 1 minus square root of 21 over 2. We will have for x squared 4 minus 5. What will be the deal over here? Again, here we will have the same situation as we had over here, except instead of the plus sign, we will have what? We will have the minus sign. So this will be 1/2 minus square root of 21 over 2. And we see this, there's absolutely no hope over here. Square root of 21 is definitely greater than 4. Square root of 21 over 2 is definitely greater than 1/2. So this number is less than 0. So there is no hope for that. Not for that root. It cannot be equal to a square root of a real number. So these are our solutions of the original equation shown over here. And now, since we solved this problem in the intended way, let us reflect on our problem-solving experience together. As the final step of the solution of the mathematical problem S2E18, let us go over the mechanics of exactly how the equation problem-solving approach was helpful in this specific case. As the equation problem-solving approach prescribes, we first introduced as many variables as needed. In our case, one variable was enough. That idea was counterintuitive at first, but later we discovered that that idea was productive as well, because the solution of the resultant equation that followed from this idea was quite straightforward. The second step of the equation problem-solving approach prescribes that we construct as many equations as possible. In this case, only one equation was enough. That equation was quadratic, shown over here in the new variable z, and its solution was straightforward. Here we show the two roots of this equation, and once we solve these two intermediate quadratic equations, we obtained 4 real roots of the equation shown over here, and that was the part number 3 of the equation problem solving approach, which prescribes us to solve as many equations as we can. It turned out that we could solve all the equations that we encountered on our journey. And as part of the solution of the equations that we constructed, we remember that we need to square, as we used to say, or validate the solutions of the equations that we obtained against the specific nature of the problem. What was the specific nature in this problem? The specific nature of this problem was the equality of these two sides, which graphically can be represented as a shifted down, horns up parabola as depicted over here, and a positive branch of the square root function that is shifted left by 5 units over here. We were expecting to obtain thus only 2 real roots, and these roots over here. The verification process was straightforward. Again, that was not really mathematics, that was mostly symbolic shuffling and computational calisthenics. And now that we understand that how we solve the problem S2M20, we can move on to the next challenge. Wonderful. Now that we're done with the challenge S2M20, let us discuss the next challenge, the mathematical problem S2M21. And I plan to title the next episode that I'll put together for you guys as Effectiveness of Advertisement, shown over here. That title is a little bit clumsy, it's a little bit awkward, but at least the title is honest, because it will completely correspond to the content of that episode. Because in the next episode we'll discuss the solution of the mathematical problem S2M21, where we are given the following setup. For example, let's say we have a company designated with the letter C. It doesn't really matter much. The company has a certain product, which I designate with the letter P, and that could be anything. It could be eggs, it could be bricks, or it could be a YouTube channel for all we care. And N sub 0 is the size of the target audience measured in people. How many people? 1,000, 2,000, 10 million, one person. Doesn't matter again, but in general that number should actually be, we'll discuss in the next episode why that number should be fairly large. And in order to make the target audience, or the audience that could be receptive to the advertisement of the product, and increase the number of people who are aware of this product, the company C carries out an advertisement campaign in which it advertises the product P. And our objective is, again, to construct a certain equation. I will not say much about what type is it, but as a hint, it will be slightly different type of equation compared to the equations that we constructed so far. So the objective is to construct a function that is x of t, where that function will tell us the number of people who know about the product P after the time t has elapsed since the advertisement campaign was carried out. Again, we suggest that you try to solve this problem in as simple fashion as possible. There are different actually ways to proceed here, but for the purposes of studying the mechanics of how the equation problem solving approach works, let us keep things simple. As simple of a model as you can, please try to put it together. And again, that function, of course, should be real. All the numbers that we're dealing with over here are real. And again, for the purposes of simplification, let us assume that we carried out the advertisement campaign only once, and in some sense it doesn't really matter. Let's say we advertised on TV, on radio, in newspapers, magazines, journals, in various posters, billboards, in different types of transportation, an airplane, train, in a taxi, whatever, over the internet. Again, it doesn't really matter. We carried out, the company C carried out that advertisement campaign once. We want to recover the shape of a function that tells us the number of people who are aware about the product P at time t after the advertisement was carried out. This is it for this episode. Thank you very much for your time. Thank you for watching. I will see you in the next episode, in which I will discuss my solution of the mathematical problem S2M21.